Hello, I am Mandayam Srinivasan speaking to you from Boston, United States. Greetings. I'm sorry I can't be there with you for what appears to be an exciting two-day agenda, but I'm happy that Professor Manivannan invited me to share some of my research experiences and in development of haptic devices and so on with you, so that I'm hoping that it will motivate many of you to start making progress in this field. Thank you for listening. The title of my talk is Hurdles in the Quest for Haptic XR plus TO. I put TO in there because what I find is XR is usually in our current vision and audio dominant world is seen as purely enhancing our perception of this extended reality. But I also wanted to emphasize that haptic, especially with haptics, it includes teleoperation as well. That is action at a distance. You operate a robot here, say, for example, and that will control another robot at a distance, maybe a continent away, that can manipulate the objects around it. So I will draw upon examples from the work we have done over 3 decades at my MIT Touch Lab, as well as around the past 10 years or so at UCL. I started my MIT Touch Lab around 1990, and and we have made progress with a variety of devices. We would like those and advanced versions of those to become ubiquitous, and hopefully this talk will excite enough of you to make that progress. After 1990, a few years later, Professor Manivannan came to my lab as a postdoctoral fellow, and together we have had these haptic adventures for 3 decades, I guess, 2.5 decades or so. And I'm very glad that he is continuing this pioneering work. Now, maybe most of you know what haptics is, but still, for those of you who are unfamiliar, I just want to give a quick intro. Haptics essentially has to do with our sense of touch. From 1900 to say 1990 or so, the term was restricted mostly to psychological study of active touch by humans. Active touch is where you, let's say, reach out and touch something or manipulate or explore an object, as opposed to passive touch, where an object comes in contact with your skin. Now, around 1990, we broadened the term haptics to include machines and virtual environments. Basically, you got PCs, and robots became smaller, actuators became smaller, and universities could afford them. So we had this opportunity to build things that were not possible before. So our working definition of haptics is it pertains to information acquisition and object manipulation through touch. Information acquisition is what is normally exploration through touch, which is you take an object, you find out its shape, softness, texture, and so on. That means you are getting information about the object. Now, object manipulation, of course, is to move the object or change its shape, say perhaps making a clay pot or doing surgery using touch. So this can be, modern haptics can be by humans or machines or a combination. It can be in real, virtual, or teleoperated environments. By real, I mean, I don't mean the Indian philosophy of Maya and so on, the sensory world that we experience today. And within that, we are trying to create another Maya, which is virtual reality. and as well as this applies to teleoperated environments as well. Now, what I'm going to talk about would be two particular cases. One is devices that enable single point touch, as if with a stick. Of course, this is touching virtual objects that are programmable under program control. And I'll particularly describe this device, the Phantom, which was built at MIT in the 1990s and which revolutionized the field. I'll also talk a little bit on another kind of touch, which is the spatiotemporal contact. It is more like what we are used to when we explore with a fingertip, where spatial distribution of forces. So it is not like feeling with a stick, but it is direct contact on the skin. And those displays, they are called tactile displays. So as I said before, so we have contributed to most of these areas over time. Haptics for virtual, we used to call purely virtual reality. Now it has become VR, AR, MR, and even XR. And then haptics for teleoperation, which is operation at a distance. It can be just across the room, or it can be across continents. Now I'll finish with what I think are frameworks for innovation, which is 5 levels of interaction that you can think of, from reality to extended reality. Now, early haptic devices, the main problem with haptics is that you want to apply forces onto the skin under program control. And for that, you need actuators, and you need something like a robotic device, which is able to alter the force, say direction, force vector direction, or distribution over time. First, we built something, linear grasper, which is like just a one-dimensional virtual reality. You can squeeze these two plates, and you can change the stiffness or damping or inertia between the two. You can make it heavier or lighter and so on. Then we built a two-dimensional version of this device, and then and several other devices which kind of could do torque and so on. But then in 1990, around 1993, in collaboration, in a collaborative project with Ken Salisbury's lab, and particularly Thomas Massey, who designed this device, the Phantom, came along. It really revolutionized what we could do. And it is essentially a desktop robot, and with a stick attached to it, a stylus, and it could move in 6 degrees of freedom. That means it can move in 3-dimensional space, and you can change the orientation. And of course, we built graphical interfaces where you could, that stick is represented by this stylus here, and you could program different objects. You could, as if with the tip of the stick, you could feel this donut, or you could feel the banana or its softness. We could feel the texture of this. So all of this could be under program control. Now, it was very successful, and the reasons why that was successful is the mechanical transparency. That means the device itself, this robot, was a different kind of robot. It was very light. And so the mass of the device and the inertia of the device was so low, and the friction was so low, that it did not interfere in feeling the forces that the object would exert on the stylus, the virtual objects. And so it had good trade-offs in terms of range, resolution, and bandwidth, and it had a good match with human abilities, which is, again, a consideration. You need to know what the human abilities are, and then you need to design the device to match it so that it can provide good illusion in interaction with virtual reality. And also because a company was started by Thomas Massey and colleagues, for researchers, it became an affordable product with tech support. And you didn't have to start from designing a robot. to do research in this field. It helped launch the field of computer haptics, what we call computer haptics, which is analogous to computer graphics, which is how to program objects that are either realistic or unrealistic as you want, so that you can explore and manipulate them. And this is what you would call a generic haptic interface. It is adaptable to a variety of chosen applications. It can be model for, say, teaching anatomy, or it can be for doing surgery, or it can be for designing a clay pot or designing shoes, for example, which it has been used for before. Now, because a company was started, they were also able to manufacture different devices. Here is a kid suddenly realizing that he is touching a virtual object that is not there. It is like ghost of an object. So they Sensible Technologies is the company, and it devised a variety of devices for users. Now, but it did not, the Sensible Technologies is no longer operational as far as I know, or it is operating at a much smaller scale. And the main reason for whatever the failure, business failure, it was very successful from a research point of view, is mainly because of low volume sales. It was successful in producing systems mainly for research clients. They had a program called Virtual Clay, where you could take clay and modify it. It is like a CAD/CAM program. And so it did not increase volume. So it helped in terms of, as I said before, shoe design or animation characters, digital dentistry, and a variety of industries. They try to go into many of these devices, many of these industries, but it was not a large volume sale. And for video games, it was a little too fragile. It was cable-driven motors with cable drives, and so that is a little too fragile, I think, for video games, where it has to be stable over thousands of cycles of operation. Now, it was also the fact that it was generic haptic device was both its strength as well as its weakness. It couldn't be easily customized to specific applications, and it was at least about $10,000, maybe even $5,000, the cheaper ones, but it was still quite expensive compared to, say, video game interfaces, which were only like a few $100s. So now the question is, would better specs and adding a tactile display, would it have helped? Now, our touch is exquisite. You can, so here is a demonstration of it. Here is Nat Derlach, my old mentor, who unfortunately is no longer with us. And he is communicating with deaf and blind people. So both of these people, they became deaf and blind when they were about 1.5 years or 2 years old. So they couldn't hear, they couldn't see, but they were at least fortunate enough to find a teacher who could train them in a system called Tadoma, where they could put their hands onto the face of the speaker, and just through the vibrations of this speaker produced, they could understand speech in real time. And to me, when I conversed with them, in fact, one of them said, Indian, he could recognize my Indian accent. So that was amazing to me. And so what it says is, if you are able to deliver the right kind of spatio-temporal signals on the skin, you can have amazing things. Now, of course, in the movies and all that, you see lots of these expressed in terms of virtual haptics or video games or minority game. What you would like ideally is you wear a glove and you can program any object and you can feel that object. But it is not so simple because there is physics involved, unfortunately. In the case of the phantom, any force that is applied on you has to have a reactive force that will be transmitted to the ground. Whereas when you are wearing a glove, any force that is applied on your skin has to be somehow transmitted to the ground or to other parts of your body, which is not simple. That kind of transmission is not simple. So that has been one of the limitations. But nevertheless, there has been lots of attempts over history in terms of tactile displays. One of the best known ones, early ones, is Braille, where you had dots and people could read text, and it's amazing speed, actually, almost same speed as our reading speed. Then the people have produced embossed maps for blind people to navigate through buildings or local areas. And there was, even in 1960s, a thing called Opticon, where you had 24 pins that would indent the skin and you could convey text information. And in our own lab, we built a 30-pin array vibrotactile display in collaboration with Professor Kyung and Professor Kwan at KAIST. Now, these were all able to produce some results, but still it needs to match the human resolution. In the human fingertip, for example, 2 points that are separated more than a millimeter away can be felt as 2 points. So if you want to have a smooth surface, these pins have to be spaced much less than a millimeter or so. Now, as I was saying, the human sense of touch is very sensitive in terms of there are a variety of receptors in the skin, and each have a certain range, bandwidth, and so on. And you need these devices to match it. And so far, our main limitation has been actuators, which are, say, motors, which are able to match the human abilities and limitations. So I would say at the present time, our tactile display status is similar to television maybe 150 years ago, where you could have an object and you had an array of sensors, and that could display an array here. And so there was also another variety of television models that were done in the 1880s. So in terms of tactile displays, basic science is reasonably well understood as to in terms of what the specifications for the devices should be. The tactile sensors, which can sense in spatial resolution, is much better. In fact, GelSight, which we worked on at MIT with Professor Adelson, can sense touch even better than humans. So that is somewhat under control. Processing also, processors, real-time processing, that's not a major stumbling block anymore because we have very fast processors. These are computer processing that I'm talking about, digital processing. And structure and transmission, this continues to be a problem, but the most important problem is we need better actuators. We need higher range, higher resolution, bandwidth in terms of frequency bandwidth, in a smaller size, low power consumption. All of these are issues at this time. I will quickly go through some of the exciting applications that are possible, some of it even today, and some of it hopefully in the future, near future. For example, this is an anatomy trainer that we developed where you can touch and feel various organs that are virtual. And so it can be a good training aid for budding doctors, I think. And we also developed some sort of an spinal injection simulator, where you can actually feel the needle going through various layers if you're doing, say, a lumbar puncture. We also developed a minimal invasive surgical simulator where you can actually feel the forces exerted by the surgical tools on the organs. I'll quickly go through because I'm running out of time. One of the other areas would be communication. That is, we demonstrated the first transatlantic touch in almost 20 years ago, um, where the phantom device was in my lab, and in Mel Slater's lab, another device was there, and together we could touch and feel each other's forces and manipulate an object. Of course, the time delays were a problem, and that will continue to be a problem. There is no getting around the limitation of speed of light, So but hopefully with good models, we can overcome some of those limitations. Mel Slater and I have also done other work in terms of communicating with rats through a robotic device. And what we need is really affective haptics, which is ability to convey emotion. And that is still a little far away, I think. Of course, in robotics, in telerobotics, teleoperation, there have been lots of advances. There is certainly a surgical system called the Da Vinci system, made by Intuitive Surgical, which is used every day all over the world. There are, of course, variety of industrial and other things. We have even built at UCL a micro nanoscale teleoperation system where you can feel micron-sized objects in real time and manipulate them. And then you have embedded haptics, where you can have various sensors. So for example, this is a robot which has a tactile sensor array, gel site, that I mentioned with you, that was in collaboration with Professor Adelson at MIT, where you can manipulate an egg and you can have a very gentle touch or a harsh touch as you need it. And in fact, the ability of gel site can be much higher than even human resolution. You can feel the fine aspects of a leaf or even bubbles and so on. Then there is the entertainment, affective haptics, where we developed a game even in 1990s where you had to move this donut along this wire, and we had two people on different sides who needed to collaborate in order to do it. In other labs, of course, there has been huggable robots, and even at IIT Madras in Professor Manivandan's lab, a virtual musical instrument was developed. And so there is a lot of scope in those areas. There is certainly industrial design fabrication. As I said, the phantom device had a virtual clay, and here is in UCL lab where they have even kind of are able to build a building with just drones, three-dimensional. So you could do that. And all of that could have haptic feedback to the user. Those drones could be teleoperated, and you could control, and you could feel those forces through a haptic interface. So let me go to and then there is also aids for blind and deaf people. Of course, just like I showed you tactile maps before, but with a phantom device, you could have a virtual map, just like you use GPS. Sighted people can use GPS and say Google Maps or something to plan their path to a certain location. You can use the phantom device and program, and you could feel the paths, and afterwards a real cane with some sort of actuator and tactile feedback can guide you to those locations that the blind person needs to go to. Then one of the applications that is really exciting, that was surprising to most people, I think, is what we did in collaboration with Professor Miguel Nicoleles at Duke University, where we were able to put a sensor array into the brain, implant it into the brain of a monkey. And as the monkey was manipulating, let's say feeding itself, then you could basically take the signals out of the brain and pass it through an artificial neural network and train the neural network essentially to predict monkey's hand position and convey that across the internet to my lab. And the phantom would be mimicking what the monkey's hand was doing. So, as I said, I think Wall Street Journal, which carried the story, is that it was as if the monkey had a 600-mile long arm. This is 600 miles, the distance between Duke and MIT. And, with also with a suitable actuator, with the suitable stimulation, you can convey that sense of touch back to the monkey brain, for example. So you could have a whole closed loop. And there are already some companies which are producing these sensor arrays that are being put into people. Let's say somebody like Christopher Reeve, who played Superman in movies. He had an accident falling from a horse, and his spinal cord was cut. Essentially, it was impaired. So even though his brain was fine, sending signals, it couldn't reach his limbs, so he couldn't move. So for people like that, you could have a parallel path. That is, you can have an array here that could sense his thoughts or what his desire was to control, and that could control a prosthetic device. So these are brain-machine interfaces that some are already in there, but in the future, hopefully a lot more that will improve the quality of life for people with, say, spinal cord injuries. So what I want to convey is quickly levels of exploration. So first, your first level is just the real world, and we are exploring, right? We are sensing and so on. So this is purely exploration, where you have sensory signals coming from the world to your brain, and you are experiencing it. Next level is, of course, manipulation, where you are activating your motor system, and you are able to manipulate the exterior world. That is the second level, which is just not purely experience, but you are also able to change your environment. And then you have third level is you have tools which have been used for millennia, where you can improve your abilities through the use of tools. So they are a layer between your brain and your body, let's say, and the real world. That is level 3. Then you have level 4, which we are now talking about, immersive interface technologies, where between your brain and the external world, where you can feel real and virtual worlds, and you can merge them, as in mixed reality or XR now, which conveys all of these. So new technologies that can enhance both our body and brain with these. Then you have further. Then what will happen, though, is that we know that brain has plasticity. That means based on the stimuli that it receives and based on its actions, its own module, software module, so to speak, will modify. Areas in the brain will modify. So brain itself gets modified, which means you create a whole new self because of these abilities that you didn't have before. So you can have, for example, real-time modeling and simulation of huge data sets. You can live comfortably, let's say, in abstract spaces of high dimensions. It is possible. Plug and play skill acquisition, for example, you can suppose learn to do surgery in much less time than what it takes right now, or learn to play a musical instrument. You can have perhaps even superhuman reach and super fast reaction time because of these technologies. And many of these are possible if you put in enough number of hours in these immersive interface technologies. Hopefully, it'll all be for the better. I'm sure there will be some bad applications as well, but that's the way the technological progress works. So with this, I conclude my talk. Thank you very much.